An assembly language is a low-level programming language for a computer, or other programmable device, in which there is a very strong correspondence between the language and the architecture's machine code instructions. Each assembly language is specific to a particular computer architecture, in contrast to most high-level programming languages, which are generally portable across multiple architectures, but require interpreting or compiling. Assembly language may also be called assembly, assembler, ASM, symbolic machine code or assembly program. Assembly language is converted into executable machine code by a utility program referred to as an assembler. The conversion process is referred to as assembly, or assembling the source code. Assembly time is the computational step where an assembler is run. Assembly language uses a mnemonic to represent each low-level machine instruction or operation. Typical operations require one or more operands in order to form a complete instruction, and most assemblers can therefore take labels, symbols and expressions as operands to represent addresses and other constants, freeing the programmer from tedious manual calculations. Many assemblers offer additional mechanisms to facilitate program development, to control the assembly process, and to aid debugging. Terminology. A macro assembler includes a macro instruction facility so that assembly language text can be represented by a name, and that name can be used to insert the expanded text into other code. By the 1970s, most assemblers were macro assemblers. A cross-assembler is an assembler that is run on a computer or operating system of a different type from the system on which the resulting code is to run. Cross-assembling may be necessary if the target system cannot run an assembler itself, as is typically the case for small embedded systems. The computer on which the cross-assembler is run must have some means of transporting the resulting machine code to the target system. Common methods involve transmitting an exact byte-by-byte copy of the machine code or an ASCII representation of the machine code in a portable format through a compatible interface to the target system for execution. A meta-assembler is a program that accepts the syntactic and semantic description of an assembly language, and generates an assembler for that language. A high-level assembler is a program that provides language abstractions more often associated with high-level languages, such as advanced control structures and high-level abstract data types, including structures, records, unions, classes, and sets. A microassembler is a program that helps prepare a microprogram called firmware to control the low-level operation of a computer. Key concepts. Assembler. An assembler program creates object code by translating combinations of mnemonics and syntax for operations and addressing modes into their numerical equivalents. This representation typically includes an operation code as well as other control bits. The assembler also calculates constant expressions and resolves symbolic names for memory locations and other entities. The use of symbolic references is a key feature of assemblers, saving tedious calculations and manual address updates after program modifications. Most assemblers also include macro facilities for performing textual substitution, e.g., to generate common short sequences of instructions as inline, instead of called subroutines. Some assemblers may also be able to perform some simple types of instruction set-specific optimizations. One concrete example of this may be the ubiquitous x86 assemblers from various vendors. Most of them are able to perform jump instruction replacements in any number of passes, on request. Others may even do simple rearrangement or insertion of instructions, such as some assemblers for RISC architectures that can help optimize a sensible instruction scheduling to exploit the CPU pipeline as efficiently as possible. Like early programming languages such as Fortran, ALGOL, COBOL, and Lisp, assemblers have been available since the 1950s and the first generations of text-based computer interfaces. However, assemblers came first as they are far simpler to write than compilers for high-level languages. This is because each mnemonic along with the addressing modes and operands of an instruction translates rather directly into the numeric representations of that particular instruction, without much context or analysis. There have also been several classes of translators and semi-automatic code generators with properties similar to both assembly and high-level languages, with speed code as perhaps one of the better-known examples. There may be several assemblers with different syntax for a particular CPU or instruction set architecture. For instance, an instruction to add memory data to a register in a x86 family processor might be ADAX, EBX, in original Intel syntax, whereas this would be written ADDL, %EAX in the AT&T syntax used by the new assembler. Despite different appearances, different syntactic forms generally generate the same numeric machine code. See further below. A single assembler may also have different modes in order to support variations in syntactic forms as well as their exact semantic interpretations. Number of passes. There are two types of assemblers based on how many passes through the source are needed to produce the executable program. One-pass assemblers go through the source code once. Any symbol used before it is defined will require errata at the end of the object code telling the linker or the loader to go back and overwrite a placeholder which had been left where the as yet undefined symbol was used. Multi-pass assemblers create a table with all symbols and the values in the first passes, then use the table in later passes to generate code. In both cases, the assembler must be able to determine the size of each instruction on the initial passes in order to calculate the addresses of subsequent symbols. This means that if the size of an operation referring to an operand defined later depends on the type or distance of the operand, the assembler will make a pessimistic estimate when first encountering the operation, and if necessary pad it with one or more no operation instructions in a later pass or the errata. In an assembler with peephole optimization, addresses may be recalculated between passes to allow replacing pessimistic code with code tailored to the exact distance from the target. The original reason for the use of one-pass assemblers was speed of assembly. Often a second pass would require rewinding and rereading a tape or rereading a deck of cards. With modern computers this has ceased to be an issue. The advantage of the multi-pass assembler is that the absence of errata makes the linking process faster. Example: in the following code snippet, a one-pass assembler would be able to determine the address of the backward reference BKWD when assembling statement S2, but would not be able to determine the address of the forward reference forward when assembling the branch statement S1. Indeed, forward may be undefined. A two-pass assembler would determine both addresses in pass 1, so they would be known when generating code in pass 2. S1B forward, forward EQU asterisk, BKWD EQU asterisk. S2B BKWD. High-level assemblers. More sophisticated high-level assemblers provide language abstractions such as high-level procedure, function declarations and invocations, advanced control structures, high-level abstract data types, including structures, records, unions, classes, and sets. Sophisticated macro processing, object-oriented programming features such as classes, objects, abstraction, polymorphism, and inheritance. See language design below for more details. Assembly language. A program written in assembly language consists of a series of processor instructions and metastatements, comments and data. Assembly language instructions usually consist of an opcode mnemonic followed by a list of data, arguments or parameters. These are translated by an assembler into machine language instructions that can be loaded into memory and executed. For example, the instruction below tells an x86 IA32 processor to move an immediate 8-bit value into a register. The binary code for this instruction is 10,110 followed by a 3-bit identifier for which register to use. The identifier for the AL register is 000, so the following machine code loads the AL register with the data 0110001, 10110000, or 110001. This binary computer code can be made more human-readable by expressing it in hexadecimal as follows. BO61 here. BO means move a copy of the following value into AL, and 61 is a hexadecimal representation of the value 0110001, which is 97 in decimal. Assembly language for the 8086 family provides the mnemonic MOV for instructions such as this. So the machine code above can be written as follows in assembly language, complete with an explanatory comment if required, after the semicolon. This is much easier to read and to remember. MOV AL 61H. Load AL with 97 decimal. In some assembly languages the same mnemonic such as MOV may be used for a family of related instructions for loading, copying and moving data, whether these are immediate values, values in registers, or memory locations pointed to by values in registers. Other assemblers may use separate opcode mnemonics such as L4, move memory to register, SAINT4, move register to memory, LR4, move register to register, MVI4, move immediate operand to memory, etc. The x86 opcode 10,110,000 copies an 8-bit value into the AL register, while 10,110,001 moves it into CL and 10,110,010 does so into DL. Assembly language examples for these follow. MOV AL 1H, load AL with immediate value Y. MOV CL 2H, load CL with immediate value 2. MOV DL 3H, load DL with immediate value 3. The syntax of MOV can also be more complex as the following examples show. MOV EAX, EBX, move the 4 bytes in memory at the address contained in EBX into EAX. MOV EESI plus AX. CL, move the contents of CL into the byte at address ESI plus AX. In each case, the MOV mnemonic is translated directly into an opcode in the ranges 88 to 80, A0A3, BOB8, C6 or C7 by an assembler, and the programmer does not have to know or remember which. Transforming assembly language into machine code is the job of an assembler, and the reverse can at least partially be achieved by a disassembler. Unlike high-level languages, there is usually a one-to-one correspondence between simple assembly statements and machine language instructions. However, in some cases, an assembler may provide pseudo-instructions which expand into several machine language instructions to provide commonly needed functionality. For example, for a machine that lacks a branch if greater or equal instruction, an assembler may provide a pseudo-instruction that expands to the machine's set if less than, and branch if 0. Most full-featured assemblers also provide a rich macro language which is used by vendors and programmers to generate more complex code and data sequences. Each computer architecture has its own machine language. Computers differ in the number and type of operations they support, in the different sizes and numbers of registers, and in the representations of data in storage. While most general-purpose computers are able to carry out essentially the same functionality, the ways they do so differ. The corresponding assembly languages reflect these differences. Multiple sets of mnemonics or assembly language syntax may exist for a single instruction set, typically instantiated in different assembler programs. In these cases, the most popular one is usually that supplied by the manufacturer and used in its documentation.